Welcome everyone. In this lecture of quantum mechanics, we will discuss about introduction to quantum mechanics and wave nature of matter. This discussion will be performed from the quantum mechanics book by March Pezer. Mass, charge, spin and magnetic moment. These particular variables are distinct properties of matter. Again, you see that mass, charge, spin, and magnetic moment. These are the variables. These are used to describe distinct properties of matter. And the point is that all of these variables seem to be of a quantum nature. So, what is the meaning of quantum nature? Quantum nature means that they take on only certain discrete variables, discrete values. So these variables take some discrete values, not continuous values. They take only certain discrete values. The notion that atoms, molecule, and nuclei possesses discrete energy levels is one of the basic facts of quantum mechanics. So, what is the meaning of discrete energy levels? Discrete energy levels means energy levels are specified in this way, that is n equal to 1, n equal to 2, n equal to 3, in this way. That means energy levels are discrete and they are not continuous. So this fact is one of the basic facts of quantum mechanics. It comes most directly from observations on inelastic collisions and selective absorption of radiation described in Frank Hertz experiment. In this lecture, we will not describe Frank Hertz experiment, but you can read this experimental procedure from any standard textbook. So this experiment is the direct evidence of discrete energy levels. Direct evidence or experimental evidence. And it can be indirectly shown from the interpretation of spectral lines that originate from the radiation from or between different energy levels. So these are the experimental evidence and indirect evidence of discrete energy levels. Consider an object as familiar as the hydrogen atom. We know that in hydrogen atom, it consists of a proton and an electron bound together by forces of electrostatic attraction. The electron can be removed from the atom and identified by its charge, mass, and spin. These variables are already discussed in the beginning of the lecture. So, we can describe electron by its charge, mass, and spin. It is equally well known that the hydrogen atom can be excited by absorbing certain discrete amounts of energy. So, after absorbing a particular energy, electrons can be excited from one level to another level, and it always absorbs some discrete amounts of energy so that it can be excited from a particular energy level, suppose n equal to 1 to n equal to 3, and that it can return by excitation energy by emitting light of discrete frequencies. So the electrons can be again come back from n equal to 3 to n equal to 1 by giving some emitting radiation. So electrons can be excited and can be de-excited, and it needs some discrete energy for this process. And when electrons are de-excited from suppose n equal to 3t n equal to 1, then they emit some radiation, and these radiation some have some discrete frequencies, not continuous frequencies. So these are empirical facts. Niels Bohr discovered that any understanding of the observed discreteness requires, above all, the introduction of Planck's constant h, small h equal to 6.62 into 10 to the power minus 34 joule second. So the fact about the discreteness which we are discussing, it needs some constant. To describe the observed discreteness, we need a particular constant, h, small h. In the early days, this h was known as quantum of action by the simple relation delta E is equal to h into nu. It links the observed spectral frequency nu to the jump delta E between discrete energy levels. So energy levels are discrete, and frequency, they also take some discrete values, and the relation between energy and frequency is this relation, it requires a constant small h, and this constant is known as the Planck's constant. So what is the significance of the Planck's constant? The significance of the Planck's constant is that it links the observed spectral frequency nu to the jump delta E between the discrete energy levels. That is, for the understanding of the observed discreteness, we need this particular constant. If we divide h by 2 pi, then we get h cut or h cross. H cut is equal to h by 2 pi appears as the unit of angular momentum. The discrete numbers nh cut being the only values which a component of the angular momentum of a system can assume. So from the Bohr's theory, we all know that angular momentum can take some discrete values. So what are the discrete values? Angular momentum is equal to n h cut. What is h cut? H cut is equal to h by 2 pi. Thus, similar to the mass, charge, spin, energy, frequency, the angular momentum also take some discrete values. Now, we will discuss about a quantum condition. Bohr was able to calculate discrete energy levels of an atom by formulating a set of quantum conditions to which the canonical variables Qi and Pi of classical mechanics were to be subjected. So, what is Qi? Qi is known as the generalized coordinate. What is Pi? Pi is the generalized momentum, and these variables are used in classical mechanics. We all know about that. So what Bohr has done, that is, a quantum conditions or quantum condition was set up. So what is the condition? The condition is that closed integration pi dqy is equal to ni into h. This is the condition. This is a particular quantum condition. But the important thing to note that this condition has been set up by using the canonical variables qi and pi of classical mechanics. These variables are often used in classical mechanics, but employing these canonical variables of the classical mechanics, the quantum condition was set up. So this relation is a link between the classical mechanics and quantum mechanics. Why? Because this condition has been set up by using the canonical variables qi and pi of classical mechanics. This is the condition, closed integration pi dqi equal to nih. The classical phase integrals for a conditionally periodic motion were required to be quantized according to closed integration of pi dqi equal to NiH. So this integral is known as the phase integral or action integral, where the quantum numbers Ni are integers. Ni can take only integer values, and we all know about H. H is the Planck's constant, and each contour integral is taken over the full period of the generalized coordinate qi. So here this is dqi. Close integration of dqi. Close integration of dqi means that the integral is taken over the full period of qi. Close integration dqi means that integration is for the full period of qi. The quantum condition gave good results in calculating the energy levels of simple systems, but failed when applied to such systems as the helium atom. But in spite of the failure, this relation is important. I have already discussed about the importance. The importance is that this relation is the linkage between the classical mechanics and quantum mechanics. During the uh, 19th century, it was believed that light has only wave phenomena. But Einstein, through his photoelectric effect, first time interpreted that light has also particle nature. Light can exhibit a particle-like nature and is emitted or absorbed only in quanta of energy. So, although it was believed that light has wave-like properties, but through Einstein's photoelectric effect, it was established that light can also exhibit a particle-like nature and is emitted or absorbed only in quanta of energy. So, what is known as the quanta of energy? Thus, the concept of photon as a particle with energy E equal to h nu emerged. So, to describe the particle nature of light, the concept of photon was introduced, and energy E is equal to h nu. This equation was emerged. So, in this equation, you see that h, that is Planck's constant, connects E with nu. So, the constant h connects the wave. Wave means nu frequency. Wave is a particular frequency, and the particle. Particle has a particular energy E. So here the importance of the constant h is that it connects the wave and particle aspects of light. This is the another importance of h. The first importance has been already discussed in the beginning of the lecture. This is another important of the constant h, that constant h connects the wave and particle aspects of light. Louis de Broglie proposed that the wave-particle duality is not a monopoly of light, but is a universal characteristic of nature which becomes evident when the magnitude of h cannot be neglected. So, wave-particle duality is not a monopoly of light. It is not the fact that only light has wave-particle duality, but this wave-particle duality is a universal characteristic of nature. And there is another important sentence here, that is, it becomes evident when the magnitude of h cannot be neglected. So, about this sentence, I will describe just after some time in this lecture. That is when magnitude of h cannot be neglected. But right now, we have to learn that wave particle duality is not a monopoly of light, but it is a universal characteristic. He thus brought out a second fundamental fact, usually referred to as the wave nature of matter. So, matter has some wave nature. This means that in certain experiments, beams of particles with mass give rise to interference and diffraction phenomena and exhibit a behavior very similar to that of light. So, in physical optics, we have studied that light exhibits interference and diffraction phenomena. We all know about these phenomena. Light can exhibit interference and diffraction. But the surprising thing is that in certain experiments, it has been observed that beams of particles, they are not waves, beams of particles, they also show the interference and diffraction phenomena. So beams of particles also show the interference and diffraction phenomena which are generally observed in case of light. Although such effects were first produced with electron beams. So here the beams of particles. So actually such effects, that is interference and diffraction, was first observed in the case of electron beams, but they are now commonly observed with slow neutrons from a reactor, but they have been exhibited for neutrons also. When incident on a crystal, these behave very much like X-rays. This means that X-ray, what is X-ray? X-ray is actually an electromagnetic wave. It is a wave. So we know that wave must show the interference or diffraction phenomena. We know about that light or electromagnetic wave exhibit diffraction phenomena or interference phenomena. So it is quite common that X-ray must exhibit the diffraction effect when it is incident on a crystal. But similar to X-rays, it has also been observed that electron beams, when incident on crystals, they also exhibit the diffraction phenomena. So diffraction phenomena is observed for X-rays, which is a wave, and it is also observed for electron beams, which are particles in nature. Heavier objects such as entire atoms or molecules have also been shown to exhibit wave properties. So this is surprising, that is entire atoms or molecules, they have also shown the wave-like properties. Although one sometimes speaks of matter waves, this term is not intended to convey the impression that the particles themselves are oscillating in space. This sentence is very important. That is, although we are speaking of matter waves, but it is not the fact that particles themselves are oscillating in space. Particles themselves are not oscillating in space. Although we are speaking of matter waves, but we have to know that particles are not oscillating in space. From experiments on the interference and diffraction of particles, we infer that the very simple law that the infinite harmonic plane waves associated with the motion of a free particle of momentum p propagate in the direction of motion, and that their wavelength is given by lambda is equal to h by p. We again see the sentence, that is infinite harmonic plane waves associated with the motion of a free particle. So we consider a free particle which is in motion and whose momentum is p. So if the particle is in motion, the particle, that is free particle, it has some momentum and it is propagating in space. So there is a matter wave corresponding to the particle, and that wave is infinite because it is a free particle. So waves will be infinite harmonic plane waves. That is the matter waves which is associated for the free particle. And the relation between the wavelength lambda and momentum p of the particle, lambda is equal to h by p. This is the de Broglie relation. This relation establishes contact between the wave and the particle pictures. Lambda is for the wave, wave properties and p is for the particle properties, and h is the constant that is used to relate the wave nature and particle nature of light. So this relation lambda is equal to h by p. The fitness of Planck's constant is the basic point here. For if age were 0, you see in this equation, if age is 0. If age is 0, then no matter what momentum a particle had, the associated wave would always correspond to lambda is equal to 0. So if age is equal to 0, then lambda must be 0, whatever the value of the momentum, and would follow the laws of classical mechanics, which can be regarded as the short wavelength limit of wave mechanics. So when age is 0, if age is 0, then lambda is equal to 0, and this limit lambda is equal to 0 means there is no wave nature. There is no wave nature for the particle, and here the laws of classical mechanics will hold. But the point is that here we are saying that if age is 0, but actually age has a particular value. Age is not 0, but in some cases the value of age may be less than the value of some classical objects. We will discuss in details later, but right now the point is that if the value of age can be neglected, although we are saying that if age were 0, but actually the point is that if we can assume that the value of age can be neglected, in that case the lambda is 0. Lambda is 0 means there is no wave nature of matter, and the laws will be governed by the classical mechanics, which can be regarded as the short wavelength limit of wave mechanics. This is the short wavelength limit of wave mechanics. In the same way as geometrical optics is the short wavelength limit of wave optics, a free particle would then not be diffracted but would go on a straight rectilinear path, just as we expect classically. You see that optics have some branch. That is, we all know about geometrical optics, and we also know about the wave optics or physical optics. In physical optics, the wave nature of light is considered. That is, whenever we explain interference or diffraction, we consider that light has some wavelength. But when we discuss about geometrical optics, then we consider that light propagates in a straight rectilinear path. That means in geometrical optics, we consider that lambda equal to 0. So geometrical optics is the short wavelength limit of the physical optics or wave optics. Similarly, here lambda equal to 0, that is when the value of age can be neglected, in that case lambda equal to 0. That means in that case the laws of classical mechanics will hold. Thus lambda equal to 0 is the short wavelength limit of wave mechanics. Similar to the geometrical optics is the short wavelength limit of wave optics. Now I will discuss that is when value of h can be neglected. Suppose x is a characteristic length involved in describing the motion of a body of momentum p, such as the linear dimension of an obstacle in its path. Suppose in the path of a light there is some obstacle. So what is the dimension of the obstacle? That is x. The wave aspect of matter will be hidden from our sight if lambda by x equal to h by xp, because lambda is equal to h by p, that is we are writing lambda by x equal to h by xp. So lambda by x very less than 1. That means lambda is very less than x. If x is the dimension of the obstacle, so value of the wavelength lambda, that is very less than the dimension of the obstacle. Lambda is very less than x. So lambda If lambda is very less than x, then the quantum of action h is negligible compared with xp, because from this inequality we can say that h is very less than xp. So in case of macroscopic bodies to which classical mechanics is applicable, satisfy the condition xp greater than h or h less than xp extremely well. So when we are describing the macroscopic bodies, such as here, when x is a characteristic length involved, and when value of the wavelength is very less than x, then the classical mechanics is applicable. And classical mechanics is applicable and it satisfies the condition xp very greater than h extremely well. To give a numerical example, we consider that at particular instant the value of the temperature is T equal to 10 to the power minus 6 Kelvin. This is the value of the temperature. If this is the value of the temperature, then in this temperature, the kinetic energy of the particle we can consider approximately as half kT. So then we'll have some value of the energy. And if we know the value of the energy, so from the relation E equal to h nu equal to hc by lambda, we can calculate the wavelength corresponding to that temperature. So if we calculate, the value of the wavelength will be approximately 10 to the power minus 6 meter or in micron order. So you see that the value of the wavelength is in micron order. So it is very less than the obstacle in the path. In for the macroscopic bodies, this wavelength is very less than x. So here the laws of classical mechanics will hold. So this is a numerical example to justify this phenomena or this fact. Indeed, the gradual transition that we can make conceptually as well as practically from the atomic level with its quantum laws to the macroscopic level at which the classical laws of physics are valid suggests that quantum mechanics must not only be consistent with classical physics but should also be capable of yielding the classical laws in a suitable approximation. So, what is the meaning of the sentence? You see this highlighted sentence very carefully. That is, quantum mechanics. Quantum mechanics must not only be consistent with classical physics. That is, quantum mechanics that should be consistent with the classical physics, that must be consistent with the classical physics, and again that should be capable of yielding the classical laws in a suitable approximation. That is, laws of classical mechanics that can be that can be obtained from the quantum mechanics. So quantum mechanics must not only be consistent with classical physics but should also be capable of yielding the classical laws in a suitable approximation. This requirement, which serves as a guide in discovering the correct quantum laws, is called the correspondence principle. So, what is the meaning of correspondence principle? It actually connects the quantum mechanics and classical mechanics and laws of classical mechanics that can be derived from the quantum mechanics. So this is the importance of the correspondence principle. Now we will learn a fact about the momentum P equal to h by lambda. From de Broglie's relation, we know that lambda is equal to h by p. So we can also say that momentum P is equal to h by lambda. Now, if a macroscopic wave is to carry an appreciable amount of momentum, as a classical electromagnetic or an elastic wave may, there must be associated with the wave an enormous number of quanta is contributing a very small amount of momentum. So what is the meaning of the sentence? If we carry, if we consider a macroscopic wave, so it will carry some momentum. So if some macroscopic wave is considered, there must be some momentum. But how the momentum will be constructed? Total momentum will be constructed. So we have to consider that the wave has enormous number of quanta or enormous number of photon, and each is carrying very small amount of momentum, so that ultimately we can have appreciable amount of momentum. So to get an appreciable amount of momentum corresponding to a macroscopic wave, that wave should have enormous number of quanta. For example, the waves of the electromagnetic field are associated with quanta or photons, for which the Bohr-Einstein relation E is equal to h nu holds. Since photons have no mass, their energy and momentum are, according to relativistic mechanics, is related by E equal to c into p, in agreement with the connection between energy and momentum in Maxwell's theory of electromagnetic field. Reversing the argument that led to the de Broglie's proposal, we conclude that equation 1.3 means that de Broglie's equation. That is, de Broglie's equation is valid for photons as well as for material particles. Because we have already discussed that is that law is universal in nature. At macroscopic wavelengths, when wavelength is macroscopic in nature, corresponding to microwave or radio frequency, a very large number of photons is required to build up a field of macroscopically discernible intensity. Such a field can be described in classical terms only if the photons can act coherently. So how we can get discernible intensity? To get a discernible intensity, there must be a very large number of photons. Similarly, when we are getting some appreciable amount of momentum, so for that purpose we require a very large number of photons. So similarly, to get macroscopically discernible intensity, we need a very large number of photons, and they should act coherently. Now, the point is that although we are saying that we need a very large number of photons to get an appreciable amount of momentum or some appreciable amount of intensity, but what is the value of the large number of momentum? Here, a surprising fact is that a state of exactly n photons cannot represent a classical field. This sentence is very important. I am repeating again, that is a state of exactly n photons. Exactly n photons cannot represent a classical field, even if n is arbitrarily large. N may be large, n may be very large, but exactly n photons cannot represent a classical field. Evidently, statistical distributions of variable number of photons must play a fundamental role in the theory. So there will not be exactly n photons. So there will be some distribution of the variable number of photons. There will not be exactly n photons. Instead of exactly n photons, what will be there? There will be a distribution of photons, and distribution of variable number of photons that will describe the discernible intensity or appreciable amount of momentum. So this is the end of the lecture. If you want to know in some more details, then I request you to go through the textbook of March Becher, that is Quantum Mechanics by March Becher and Eugen. And thank you everyone who have listened this lecture.